Hello, so I was studying about LET, that is linear energy transfer, RBE, relative biological effectiveness, and OER, oxygen enhancement ratio. So we'll study about this in detail, but before that I'll be telling a little bit about ionizing radiation, which are less ionizing, heavily ionizing radiations. Okay, so we know that X-rays and gamma rays these are photons, so they do not have mass. As you increase the size, then electrons comes, and protons, neutrons, then the uh, helium. Helium is an atom, right, uh, with a atomic number of 2 and atomic mass of 4. So yeah, so these are less ionizing, these are more ionizing if you take it that way. So um, if you go by this, so these are less ionizing and these are densely ionizing. So you can consider this is alpha particle, this is neutrons, this is protons, electrons, and these are X-rays, gamma and the X-rays. So whenever I say dense, like highly ionizing, this is less ionizing, this is highly ionized. Whenever I mention highly ionizing, then you have to consider it's either neutron or helium. Less ionizing, then you have to consider for gamma rays or X-rays. Also, you have to understand that for X-rays or gamma rays, when they are traveling through a medium, so if you start from there, so they will travel deep, right? They will travel deep, but on the way when they are depositing their energy, they will be depositing their energy like very sparsely distant, but less energy deposition, but it will travel a long way. But if this will be for X-rays or gamma rays. Now if you take for neutrons, like heavy particles like alpha, they will deposit a large amount of energy wherever they go, but it can't travel much. We know that it's heavy particles, so it can't travel much, but wherever they travel, they deposit a lot of energy. Okay, so these are densely ionizing. Okay, and the energy which they deposit will be more wherever they travel. Now the example of that is like if this is the DNA segment. Okay, 1 second. So if I have to add, so this is the DNA segment. Now this is an X-ray beam. So due to the interaction, whatever the electrons are produced and the deposition of energy, it's like that. So these are the interaction sites where it happens. This is the X-ray beam. So this is the point of action. This is the point of action. Those are the interaction sites for an X-ray beam. Those are the electrons generated, and those are the interaction site. But if we consider a neutron beam, so the electrons generated from the recoil of the protons due to a neutron beams are like that. So the energy, the interactions with the neutrons are so that's what I meant earlier when I say less ionizing, it should be X-rays, and when I say densely ionizing, it should be neutrons or something like that. Now this is the same image, same information, but this is a electron micrograph where you can see this is some organelle. So you can see this is like very dense white, which you are seeing, or for a proton, the deposition which is happening, the densely energy which is deposits for the which is seen through the electron microscope. And you can see faint lines or faint dots over here, these, and you can see faint dots over here, white dots. So it is like there is a lot of distance between each of those. So these are like sparsely ionizing, and this is densely ionizing. That's the example, and this is an example seen on the electron microscope. Now what is LET? Is linear energy transfer. So as the name suggests, it's on the linear axis and the energy transfer happening, but it's the energy transfer per unit length of track. So for example, if this is the track and you are giving x-rays or you're giving neutrons, so how it travels over 1 unit length of track, this is the track, so it has to go this way. So in that, on 1 unit length of the length, how much energy is being deposited so that is linear energy transfer. Okay, so the unit of linear energy transfer is kilo electron volt per micrometer. So every for 1 micrometer, how much is the, so if you take a distance of a 1 micrometer, how much is the energy which is deposited at this, energy which is transferred from the neutrons or x-rays to the medium. So that's the linear energy transfer. So this is linear energy transfer. It's usually for the charged particles, and that is what is transferred to the medium is what is calculated. And the formula for this is L is equal to dE by dL. That's the change of energy, and that's the length. So LET is an average quantity because at the microscopic level the energy per unit length of track varies over wide range. Also you can calculate this by track average or energy average. So you can keep the track length as same, the unit length will be same, and then you're trying to see how much the energy has been deposited. So it will be more in some cases in 1 unit, and there will be less in another unit. There will be 3 over here, there will be again 2 over here. So it's like the length is constant, and then you're seeing how much energy is deposited in 1 unit length, and then you take an average. So this is track average for LET. And then or you can take also called as energy average. In this energy average, what you're doing is you are trying to calculate trying to calculate how much. So this is 4 energy, right? 1 2 3 4. If you're putting lengths for that, so here the length is small, here the length is big, here the length is average. So but you're taking the same energy level over here. You have taken the same length level, and here you're taking the same energies, what is that, and the length is the one which is varying here. So this is energy average and the track average. LET is basically the average energy deposited per unit track of time, measured in keV per micrometer. So this is the image which is there in textbooks, the LET, and this is the track average which you are taking for the same length, and then you're counting the energies per unit length, and then you can either take energy average where the average energy is the same, and then the length is different, so you can take average of that as well. So yeah, so this is a box which says the linear energy transfer. So as I go from gamma rays, x-rays till the alpha particle, neutrons, the linear energy transfer increases. So it is 0.2 here, it increases to 2 here, it increases to protons over 4.9 here. When it comes to the alpha particles, it's more. So you can see the linear energy transfer for the densely ionizing, it kind of increases. For neutrons, they have divided into track and energy average. For track average, it's because neutrons do not travel much, right? But if they travel, then the energy deposited at one point will be more, but the track average is 12. So the basic concept is like from the less ionizing to highly ionizing, if you go, the linear energy transfer increases. Okay, now next is RBE, that is relative biological effectiveness. So as the name says, it's the relative biological effect that we are calculating here. So like from less ionizing to densely ionizing, if you're comparing, so RBE, the formula is dose of the reference radiation divided by the dose of test radiation. Okay, so it's the ratio of the doses required by two different radiation to cause the same level of effect. Okay, so it's just like measuring, like if you're using some kind of X-rays, and if you're using neutrons, obviously neutrons have a more linear energy transfer and lesser than the X-rays. So if you use 8 gray of X-rays to produce this X amount of biological effect on a particular tissue, then what amount of gray in neutrons is required to produce the same effect? Obviously, logically, the amount of neutrons required to produce the same effect will be lesser compared to the X-rays, because obviously neutrons are more densely ionizing. So you will need lesser amount of neutrons to produce the same effect than the X-rays. For example, if 10 gray of, like from cobalt 60, if you take gamma rays to kill 50% of cells, tumor cells, then 1 gray of some kind of heavy ion which we are using, okay, that will take for again 50% of the kill. So the RBE will be 10 by 1, which is 10. So 10 for our reference radiation, and this is what we are testing. Whichever heavy ion that we are testing is 1. So only 1 gray of this particular heavy ion is required, as opposed to 10 gray of our usual gamma rays. So this is a typical survival curve, and so usually we do not see these neutrons, right? This is usually the surviving fraction on the y-axis, and the dose on the x-axis is what we usually see. And yeah, we usually don't see these neutrons. Now for the comparison, we have put this here. So for X-rays, we know, like as the dose increases, the surviving fraction will decrease. So initially there were 10 number of cells. So like this is logarithmic scale. So you can just imagine how much the surviving fraction is decreasing. So the cells which are left behind or surviving are lesser here. So it is 10 here, 1 here, 0.1 here, 0.01 here, 0.03 here, or something like that, right? So for X-rays, as it increases, as the dose increases, the curve is kind of like that. And logically, like we explained, for neutrons, lesser amount of the dose is required to get the same effect, to the same fraction. So to get the number of cells to 0.01, to this surviving fraction, this is 0.1, 0.01, yeah. So to get the same effect, you are giving around this is the dose is in rads here, so you're requiring lesser number of neutrons compared to the X-rays. So you're needing 1200 rads here, and here around 600 or something like that. So the RB, the difference what is required is 1.5 for the neutrons here. So RBE will be 1.5. Okay, the 1.5 amount of what effect we got with the X-rays. And but when the cells were more, this is the lesser surviving fraction, right? When the cells were more, the RB difference was more. So when the cells are more, then the neutrons had a better effect compared to when the surviving fraction was less. So here it is like RB 3 by 1. So so neutrons required more here compared to the X-rays. So X-rays, if you had if you if you require three times of X-rays to get the same effect as one time of neutrons. Here it is, you require 1.5 times of X-rays to get the same effect with one time of neutrons. Basically what it is like, as the dose decreases, the RBE increases. So here the dose is decreasing, the RBE is increasing to 3. Here the dose is less where RBE is less. Okay, that's the basic point. Now the thing is, this is for single dose fraction. This is for single dose. Now if you take for a fractionated dose, now if you're giving in 4 fractions, you're giving in 4 fraction, we are comparing the same RBE in this. So here if you're giving in 4 fraction, to get the same effect, as 0.01, like 10 to the power of minus 2 effect, if you're giving in fractionated doses, the RBE is more. The RBE is 2.6. So you require more number of X-rays as opposed to neutrons when you're giving in fractionated dose. So the basic was dose. As you increase the dose in fractionated, the RBE increases. So as you're increasing the dose, the RBE is increasing here for the fractionated dose, but here in the single dose, as you increase the dose, the RBE is decreasing. See, you can see the RBE was more here, it was 3 here, and as you increase the dose, the RBE decreased, right? So in fractionated dose, as you increase the dose, like you can see the difference over here it was less and here it is more. So the RBE is more as you increase the dose here. So basically what we are trying to tell is the net result is that the neutrons become more progressively more efficient than the X-rays, as the dose per fraction is reduced. Here in one fraction there is more dose, that is why it is a single dose, right? Here in one fraction dose is less, and the number of fraction, if you increase, the RBE will increase. So basically with fractionated doses, neutrons are like progressively more efficient. That's what we are trying to say. Okay, another concept is, so this is a graph for, this is LET, so this is LET and this is RBE, right? This is that one hit with the X-rays, but this is like multiple hits. This is the more energy deposition. So as you increase the energy from lesser energies to lesser ionizing to more ionizing, so this is more energy deposition over here, and this is less. So this is what we don't require, like this is lesser and this is more than what we require. But what we need is this optimum damage, like the double strand break that we need this is the optimum, and usually the optimum LET is at 100 keV micrometer. So the relative biological effect, it increases as the linear energy transfer increases. So this is for X-rays, and this one if you just take for neutrons. So lesser ionizing, the RBE and LET, so it increases. So as you increase the LET, so this is coming to the increasing ionizing, so the RBE will be most for around 100 keV, and then after 100 keV per micrometer, the RBE also decreases. So this is the most optimum LET which is required. Again, this is the linear energy transfer and this is the RBE. So yeah, as the this is the optimum LETs at 100 keV micrometer, and anything more than that is overkill, anything lesser than is less efficient. So this is the optimum LET. So optimum LET deposits the right amount of energy per cell, which produces just the enough DNA double strand breakage kill for the cell required, like I showed in the previous image. Now OER, that is oxygen enhancement ratio. So oxygen enhancement enhancement ratio. So as the word suggests again, how much of the oxygen enhancement is required for hypoxic cells. So OER is like radiation dose in hypoxia by radiation dose in air. Okay, so if there's a hypoxic cell and this is an oxic cell, hypoxic cell and oxic cells, so how much of oxygen is required, more oxygen required for the same same effect to be produced by the same radiation, for the same effect to be produced, that is the oxygen enhancement ratio. So like again using the same common sense like I discussed in the earlier. So less ionizing and highly ionizing. So for less ionizing, OER will be more, because for a hypoxic cell with a less ionizing it will need more OER, but if it's a highly ionizing radiation, then not much of oxygen enhancement is required. Only highly ionizing is enough to produce the same effect. So OER will be more for less ionizing, it will be lesser for highly ionizing. I'll show that in a graph now. Okay, the same thing that I said now is, this is the radiation dose in gray and this is the surviving fraction on the y-axis. So this is for the hypoxic cells and oxic cells. So oxic cells, they have like some good oxygenation. So as you increase the dose, so much of like surviving fraction is like the surviving cells are becoming lesser and lesser and lesser with the increased dose. So as the surviving fraction decreases, the dose required is a little bit more. But if you take hypoxic cells, the dose required is very large. So you can see here it is like 11 to 12 which is required for surviving fraction of so much. But as high for in hypoxic cells, we need more dose, like it is like 15 here, it is 30 here. It is kind of double. So the OER which is required is 2.8 times for the hypoxic cells compared to the oxic cells. And in this graph what they're trying to say is, like, this is X-rays, that is less ionizing, and these are alpha rays, so this is highly ionizing, right? So you can see the difference between for hypoxic, this is hypoxic, for oxic. So you can see the how much enhancement is required for in case of less ionizing. So as you increase to more ionizing, you can see the gap being decreased. So this is like neutrons and this is like alpha rays again, but it is of lesser energy alpha rays. So so as you see, you can see that the gaps required is much smaller. So with very high LET radiation, the oxygen effect is kind of non-existent. So in this, like, it is not existent only. So the gap is so less, like as the dense ionizing increases, that there is no difference itself. The basic common sense again is for a lesser ionizing, the OER will be more, and for highly ionizing, the OER will be less or like non-existent. Okay, if you're trying to compare LET for the OER again, like I said, so this is less LET energies, this is for X-rays if you're taking, and neutrons here and then alpha here. So as you increase the LET, the oxygen ratio which is required is more. Here you can see like 3 into 2.8, so it is like 2.8 here. So between 3 and 8. So as you increase the energies, the oxygen enhancement ratio required is lesser. So once the LET is more than 100 keV, then the oxygen requirement does not matter. So it is non-existent beyond 100 keV. So it kind of starts decreasing after 60 keV or something. So it will be kind of okay-ish, like similar until 60. After 60 keV it decreases, and after 100 it is almost non-existent and does not depend on oxygen enhancement ratio. Now this is the final graph which we have to understand, and this is important. For this we had to know all of the concepts before, that's why I had to tell all of that. So yeah, so if you are considering so LET is here on the x-axis. As the x-axis increases, LET like energy is increasing on this axis, and this is RBE on this axis, and this is OER on this axis. Okay, now so we know that this is like the combination of all the graphs that we have studied until now. So as the energy, so if when I'm saying lesser LET, you have to imagine it is X-rays. When I'm saying more energy, you have to imagine it is neutrons or alpha particles. So like I said, as you increase from the X-rays to neutrons, the relative biological effect will keep on increasing until it reaches a maximum for 100, and after that it decreases. That is for RBE. This is the curve for RBE. Okay, now coming to the curve for OER. So it will be more oxygen enhancement ratio. Oxygen required for hypoxic cells will be more for the lesser ionizing, like X-rays, like it's starting from here, right? So it is more for here, and as the LET increases, as it goes to neutrons or alpha, the oxygen enhancement required is lesser until it reaches 100, and then after that it becomes not required, so non-existent. So this is just the addition of all of that. So this is the curve for OER, this is the curve for RBE, and that's the summation of all of it.